Here we're going to look at the energy of an orbiting object. So if we put an object of small mass and it orbits in a uniform circular path at this location, of course it has a tangential velocity and it is some distance away from the planet. So it has both kinetic and potential energy. So the total of the kinetic plus the potential will equal the total. And at that location, we have to use the distance from the center to the orbital radius. We also know for an orbiting object that the speed that it orbits at is shown from that equation. Now, we have velocity and the kinetic energy, and if this is orbiting in uniform circular motion, this is the equation that solves for that velocity. So by squaring both sides and substituting into the kinetic energy equation, we get G big M times little m divided by the 2 over R. We can see now that the total energy is equal to half of the original potential energy. If we go back and look at this equation, we now have that the kinetic plus the potential is going to equal the original potential over 2. So if we move this over to there, we get that the kinetic is equal to negative U over 2. Or stated another way, that the total energy is equal to the negative of the kinetic energy. Now, let's look at a situation where it's not uniform. So if our orbit is elliptical, actually we'll just put an object there, give it some kinetic energy, and it has some potential energy. If this velocity is not large enough to maintain this orbital radius, it's going to drop closer to the planet, which will cause it to have an elliptical shape. As it falls towards the planet, the velocity will increase. We can see that here. So if the bottom value goes down, the velocity goes up. But what we know about every location around that ellipse is that total energy at one point is equal to the total energy at the other point. I'm going to get rid of some of this stuff here. All right, so point 2, the object is closer, so we'll call that distance A. And if the energy at point 1, you'll have 1/2 mv1 squared. And again, v1 is going to be smaller than v2. And it also has its potential at r. That'll have to equal the 1/2 mv2 squared minus the potential at A. It really is set up just like any typical energy problem. There's no energy added or lost since there's nothing it's interacting with from the outside of that system. And that was for if an object was moving too slow for that radius. A similar thing would occur if it was moving too fast at a point. It would just fly further away.